Hello everyone, we're ready to start. Today we continue with the transport layer and hopefully finish it. And tomorrow we meet again for a test and a lab. We have seen that TCP requires a connection establishment. This is showing the server side here. This is showing the client side. The client sends an initial packet, connection opening packet called a SYN packet. This is an empty TCP packet that contains no data, but only a sequence number and the SYN flag in the packet header. It is expected that the server responds with an acknowledgement of this packet and a SYN packet that has the effect of opening the connections in the reverse direction. And at this point, in principle, the connection is established for the server. Already at this point, in principle, the connection is established for the client as well. That's the way TCP works. This is called the handshake. It's called a three-way handshake. There are three messages that need to be exchanged. Only then can data be sent. Although in theory you could send it already here, but only then can the data be sent. Those messages are TCP empty messages, but they are TCP segments. They are subject to retransmission, the way we saw it before. So for example, if the SYN that is sent is lost, then a timer will expire at some point, and no ACK will come, of course, and then the source will retransmit a SYN. Similarly, for any of those packets in the exchange. What's the value of doing this? Why do we have this fairly clumsy procedure? Why can't we simply say, if I have something to say, I open the connection and I start with initial data? Why don't we do that? Yes?
Because you're not sure that your message arrived in the first place. You're not sure that the host is ready to listen to you.
You don't know, you're not sure that this host is ready, but if this, sure. But if you will see, if you receive an ACK, you will know it was ready. If you don't receive an ACK, you will try to retransmit and probably time out after a number of retransmissions. But the same can happen here. You can send a SYN packet. This guy is not ready to receive it, and the SYN packet will die. Yes?
You can measure the round trip time?
You can measure the round trip time. That's a good argument. But you already need an estimate of the round trip time here for the timeout here. So you need a conservative estimate of the round trip time to get started. So you would have a chicken and egg problem. That certainly simplifies the retransmission for subsequent packets, but still one could imagine sending some data in the first segment here. But it's not done. It's never done. Is there a good reason for that? Perhaps there is no good reason. Yes? The sequence numbers have to be set up, it's correct, but they're implicitly set up here, right? When you send the first sequence number, then you know it here, right? But originally, that was the idea. The original idea was to be able to make sure all the sequence numbering is okay. Later, there is another good argument for keeping this way of doing. It is verification that the source really exists from the server viewpoint. The weak part in the internet is the server. If you want to attack something, you attack the servers first. So if you're a server and you receive a SYN packet, so somebody is saying to you, I want to do some TCP with you, by sending a SYN ACK and waiting for this to happen, you are sure that at least somebody that responds to the IP address that was in the source field and the source port number exists and is responding with that. We could do a SYN flood attack to a server by sending a huge number of SYN packets, and if these SYN packets would cause the server to start doing some work, then that would be a very easy way to force a server to do a large amount of work. Right? Imagine, for example, you send a GET for a video file of 1 gigabyte in the first message, then the server would start downloading it, but perhaps there's nobody doing it. So that's one of the interests of this, which is the verification that a client really exists. It's a weak form of verification, but that's a justification for keeping this handshake. As we will see, this handshake is a problem, and a lot of work has been done at avoiding the handshake to speed up things. This is the TCP segment header that we've already discussed. The sequence number and the ACK number are always in the header, so the SYN packets, for example, have no data. They just have TCP headers. As a programmer, if you program using bare-bone TCP, like we will do in Lab 3, this is what you see. That's what is visible to you. On the client side, like with UDP, you create a socket, you bind to it, and then before sending any data, you need to do a connect call. Connect has the effect of doing the three-way handshake. On the server side, you do similar thing. You create a socket and bind it to the server port, typically here. And then you do a new call that is not visible with UDP called listen. Listen means I am ready to receive SYN packets. And this has arguments like the size of the queue of SYN packets that you accept to buffer if you're not able to process them immediately. And then, if you want to do some useful work, you do an accept call. Accept means I am willing now to open a connection for somebody who has sent me a SYN packet. So the accept consumes one of the SYN packets that has been received by the machine and opens the connection here. The specificity of TCP is that when you do so far we have not sent any data. Now what happens next depends on the logic of the application. If you use HTTP, this is what happens. The next thing is the client sends a message. The message is an HTTP GET, for example. But this is not necessarily always the case. There are applications where when you open the connection, the first guy who speaks is the server. It depends on the application. Those applications are sometimes more difficult to handle, but they exist also. On the server side, when you have accepted the connection, and when the connection has completed, that means the SYN ACK, and ACK has been received, then you can start doing things like receive data. Receive is the equivalent of read. But since you know on which connection whom you're reading from, you don't need to pass arguments like whom you would like to read from, or you don't need to have return arguments saying who sent you the data. And the pink thing here means this is a different socket. So the dotted line here implies that the server creates a new socket, which is here described with the pointer S2. So S2 equals accept, means the accept call does two things. First, it does the handshake, and it forks the socket. It makes a clone of this socket to another one, to which the server is also connected, on which the data will be received. This means that TCP always requires a different socket to receive the SYN packets and another one to do the job once a connection has been opened. This is a very simple server that receives the data, does the job, and when the job is done, closes the socket and comes back to accept another TCP connection. Of course, a web server does not serially handle the clients. If you would do that, you would be very slow. So what is typically done is once a server has accepted one connection, it forks a socket, does the work on this socket, then the code is typically using some form of parallelism, threads typically, such that on a new thread, you fork this socket, and also fork a thread on which you will be able to process it, while in parallel, you can come back and accept a new connection. So a typical TCP server may have a large number of TCP sockets open. All of these sockets are open on the same port that the server is listening to. For example, port 80 for standard HTTP server. So you have multiple sockets listened to handled by the same server program. This is how the operating system mentally views those sockets. So I'm showing here, so as usual, the IPv4 and IPv6 world are treated differently, even though the TCP is the same. So software is the same, but it has different namespaces for the different sockets. And the SYN packets are handled by a special socket of this server program that is also sometimes called an unconnected socket. That's the socket on which you receive the connection opening request. So itself, it is non-connected. And as soon as one connection is open, there are creation of one new socket. So the data will go to this or that socket. How does the operating system know that a TCP segment has to be delivered to the buffer of this socket or the non-connected socket? Yes?
Checks whether the packet, the segment contains a SYN flag.
Exactly. So here, if there is a SYN flag, you know certainly you have to deliver it here. And if there is a SYN ACK, it's a bit more complicated. The SYN ACK is associated with the SYN ACK. That the ACK of the SYN ACK is associated with the SYN ACK that has been received, and it's only when you receive it that the socket is open. So the creation of a SYN ACK is a special case that when you receive, an ACK that follows a SYN ACK of this, you have to create the socket here. So this is a special case that is not shown here. Thing to remember is when a server accepts a SYN packet, in principle, with this simple image, it needs to remember some state information. When it has accepted a SYN packet, it sends a SYN ACK and waits for the response of the SYN ACK so it knows which sequence number is expected. And in the SYN packet, there may be things like options. For example, what is the maximum packet size that may be sent in the first SYN packet that needs to be remembered. So this state information is a potential weakness for servers that we will discuss a bit later. We use the word segments for TCP packets or TCP PDUs. So a TCP segment is the thing that fits in an IP packet that contains the header that we've seen is 20 bytes plus options and the TCP data. The TCP segment has to fit in an IP packet, and the choice of how to create segment is done by TCP. Question?
On the previous slide, how does the OS know to which socket to send it? I mean, not the SYN and data, but two different data of two different sockets. How do you know where to send it?
So here, how does it know it has to go here and not there? How do you think?
Well, looking at the IP and port from source.
Exactly. So a socket is associated, it is a non-connected, or is associated with a remote peer. So a socket is associated with the source IP address and source port number. So for every different combination of local source ports, local IP address, and remote source port, remote ports and IP addresses, there's a different socket. This one is associated to no remote system. So this is how the operating system can decide to which socket the data is delivered. Yes? If you have multiple sockets with the same, in principle, it's not possible. In principle. So when you bind, when the server program here will do a bind to this socket, if another server is doing a bind to the same, does a bind to a port number, local port number of this socket, if another program is trying to do it, it will not accept it. For example, if you have two web server programs on the same machine, the first one will bind to port 80, the second one will not be able to bind to port 80. So you will give it another port number, 8080, for example, or something like this. So in principle, it's not possible because of this principle that a socket is identified by the 4 tuple of the source and IP addresses on both ends. Question?
Is that up to the operating system to forbid or allow the socket to be used?
Is it up to the operating system? Perhaps. Perhaps you can invent a new machine that will allow multiple, perhaps it's even possible, I don't know. But certainly there is a problem with knowing where to send the data, right? The data essentially would have to be duplicated. I'm not saying it's impossible to do. In software, you can do whatever you want. But in principle, if you do that, you're doing something very weird. Perhaps it's a good idea for some purposes. But, yes?
So there can only be one SYN socket for each port, but there can be multiple data sockets for each port.
Yeah. Here is shown there is one non-connected socket, and there are two open sockets. So this server is talking to two remote clients. For example, it's a web server that's talking to two remote clients and is ready to receive further connection open requests. Okay. Other questions? No. So it's TCP that decides how to create an IP packet. It's not the application, right? This is first important thing. So if you write a program that does, for example, read from a file 1 byte, send it over a TCP socket, and you do that and you have 10 million bytes, so you will do 10 million reading of the file and send it on the TCP socket. Sometimes you do that if the file is, for example, a stream that comes from an interactive input. You don't know the end of the file, so the only thing you can do is get the data one by one. Then very probably your local implementation of TCP will not create one TCP packet for every byte that you're sending into the socket, because it will implement an optimization algorithm that will say, well, this is very inefficient to send the bytes one by one if I have some evidence that the application is doing a lot of repeated write operations. So it's TCP that will decide when to segment. So typically in a case like this, it will find a trade-off between waiting. You will wait a very short amount of time for on the socket buffer side, right? This is a two-way socket, so the application is writing into it. If you see an increment of 1 byte, then the operating system will wait perhaps 1 millisecond before sending the byte. And then in 1 millisecond, if the application is fast and has done many writes, there will be more than 1 byte. So it's TCP, or the implementation of TCP in the operating system, that chooses how to segment the data. I've spoken of the example that the data is too small to be reasonably sent in 1 packet per 1 write. The opposite, of course, occurs. You could have an application that writes a block of, for example, 4K bytes, and the maximum packet size that's available in this machine, or better, on the end-to-end path, is smaller, so it would not fit in 1 IP packet. So a rule of thumb, not a rule of thumb, a rule of the internet, is that TCP should never create segments that are too large to fit in an IP packet. So we'll talk a bit about that a bit later when we talk about fragmentation in the internet. If IP packets are too large somewhere, they might be fragmented, but if the packets are sourced by TCP, this ideally should not happen, because TCP is able to handle the optimal thing here. The minimum packet size depends on the version of IP. For IPv4, it's 500 bytes around, and for IPv6, it's 1200 bytes. Right? So you can make the assumption, if you're a TCP application running on IPv6, you can make the assumption that 1200 bytes are safe. You can always create packets of 1200 bytes. If you want to send more, you will need to test whether the end-to-end path is able to have this packet length. A few optimizations that I will skip here, but you can read it. The effect of this, or the root cause for that, is, if you remember, that TCP is designed to offer a streaming service. So the goal of TCP is to deliver all the bytes that were written into the socket to the other end in exactly the order that they were written and without any loss. Yeah. That's called a streaming service. A stream is a succession of bytes in the TCP/IP terminology. On the receiver side, typically, data accumulates on the receive buffer until the application reads it. So that's the dual of what I've discussed on the sender side. On the sender side, it's TCP that decides how to create packets. On the receiver side is the application that decides how to read the data, how many bytes you want to read from the buffer. But since it's a stream of bytes, there is no marking of end of frames or things like this in the receiving side. So it means, in particular, if you have an application like, for example, say, PMU, a sensor that sends a measurement every second or every fraction of a second, and if you send that with TCP, there is a possibility that if there are losses and a message is retransmitted, for example, that two messages are glued together by TCP. So on the reading side, if your application is now reading from the TCP socket, it should not simply read and get all the data that's present in the buffer, because this all data could contain one or several messages. Or at least if you read all the data, then you have to analyze the data to find where is the beginning. Is there only one packet, one application data packet, or are there several application data packets? In other words, the marking of where an application PDU starts and ends must be done by the application itself. Yes?
Why would we take this approach instead of UDP and application deciding?
Why did we take this approach? We took this approach because TCP offers a streaming service. So we can do a matrix of design criteria requirements. We can say, I would like to have a transport layer that is reliable and message-oriented, or that is reliable or streaming, and I could do a non-reliable transport layer that is message-oriented or streaming. You could have those four combinations. It turns out that in the internet, only two of those four combinations are offered today. UDP, message-oriented, non-reliable, or TCP reliable, but stream-oriented. There are other protocols that have been invented, like I'm not sure about the acronym, don't want to say something wrong. There are other protocols that have been invented that do a message-oriented, reliable protocol. They exist, but they're not used. So for various reasons that we might discuss a bit later. When we talk about the application layer, we'll talk about QUIC, which is trying to solve some of these problems. This is how TCP is, and it's very important to understand that it is that way. Right? A side effect of this is called head-of-the-line blocking. The first side effect is that the application needs to mark where things stop and end. You cannot rely on the fact that some data has arrived in a socket to conclude it's a new application PDU, for example. But that's not a big deal. In principle, any application always has a framing system. For example, if you send a file, if it's an image, you will have a MIME header to say this is an image. So you expect, when you have a response to an HTTP GET, you expect to see a MIME header coming from this. So from the MIME header, you will see what's inside. So this is taken care of by application layer formats. But this is more embarrassing. Head-of-the-line blocking means that if you have one application like HTTP, the current version of HTTP allows to transfer multiple objects on the same TCP connection. If you go to a web page, typically this web page may have multiple objects. Well, why is that? More efficient loading, but also because the page typically contains several things, like it may have graphics, graphical elements that are separate files. It may have a pointer, an iframe that comes even from another server. So a modern, an old style HTML page was one HTML file. Newer HTML file will have page will have an HTML file that may have scripts that themselves are not in the page but need to be downloaded from a server, images, objects, etc. One way to handle that is to open one TCP connection per object. This is HTTP1 doing it that way, but this has a drawback. What is the drawback? overhead. Which overhead?
Opening the TCP connection for
Exactly.
potentially small amount of data.
Opening the TCP connection, exactly. So opening a TCP connection for every small amount of data means a three-way handshake for every small piece of the page. So that's very inefficient. There are other reasons that we will see a bit later when we talk of congestion control. When you open a TCP connection, the rate at which you can send on this connection is very small at the beginning, to be conservative, to make sure you don't flood the network. So, and you increase the rate during the TCP connection. So if you open lots of TCP connection, you always start small. So it's more efficient to open one connection. If you have a good connection, the rate will be fast, and then all the subsequent elements will come fast. So this is why HTTP2 allows multiple objects to be sent over the same TCP connection. And you see that if you have a complex page, you see that it starts displaying, and the display changes as the images are received. For example, if the size of the image is not known in the HTML file, then you cannot display it as it will be in the final format. So that's visible to us. Now, what happens if a packet is lost in one of the embedded objects? For example, a packet is lost in an image, and most images on a web page have no interest. They're just decoration or worse, advertisements. So if a single packet is lost, then all the things that are behind it are not delivered to the application. So if you lose one packet while transferring an image for a stupid decoration, then your page doesn't load. It will wait. The HTML, your navigator, your web client, does not receive the data that were sent after the image. Even if it's a huge set of data, you have 10,000 packets, one is lost, the 10th one is lost, but many other packets were received. For example, the following script might be entirely received and could start executing on your page, but it won't. That's called head-of-the-line blocking, right? That's in the streaming nature of TCP. How could you solve that?
By opening more connections?
You could open several connections, or you could invent a new version of TCP that would allow multiple streams inside the TCP connection, right? This is what Quick does. We'll talk a bit later. For which of applications is the streaming that I've discussed here really a drawback? There is a typo here with one. Of course, right. So option B is HTTP2 is one TCP connection in total for all object transfer. I close the poll. And as a short majority says, it's B and C. If you open one TCP connection, an app using HTTP. I'm sorry, I'm very sorry, I've confused you a lot. So an app using HTTP with one connection, is it a way to in total? And do I have the eraser? Well, perhaps you want to correct your vote, but the clear message is an app that uses HTTP with one connection in total will suffer from the streaming service. No, sorry. I think it's time for lunch for me. An app HTTP one with one TCP per object, that's correct. That's correct. So, and this is one TCP connection in total. And as usual, the majority is right. So F is the correct answer. Streaming application is an interesting example where the streaming services is not adapted to a streaming application, or at least a real-time streaming application. A real-time streaming application is, for example, an industrial process where you measure something. Chemical reactor, you measure the pressure, the temperature at 200 points. You receive the 200 measurements every 10 milliseconds, for example. You take a decision based on that, and you continue. Now, if you send those things over TCP and one packet is lost, what will happen? On the sender side, the TCP will try to retransmit the missed data. And it will do that at the expense of transmitting new data. So if the application has delivered a new measurement, but the old one has not yet been hacked, then it will retransmit the old measurement, which makes no sense for the semantic of the application. If you're doing hard real-time control, the application prefers to have one missing data. I mean, if it arrives late and there is newer information, then you prefer to have the newer information than having the old one. So for those streaming applications, this is not adapted. Yes? Why is it a drawback for B? Because you have that's what we explained just before. If you have HTTP2 and you use a single connection for transferring all the objects, and assume, for example, you have a web page that has a banner at the top and a few scripts, and the first thing that is transmitting is the banner, and the script takes some time to execute on your machine. If a byte is missing in the banner, the script is not delivered to your application. So your web page does not even read the script. So you will have large delay, which is completely unnecessary. If you had one stream per object, you would have a banner that you see is not yet fully visible, but the script would start to execute, and perhaps the script is the major part that is organizing the page and takes some time to compute, which may in turn contact other servers, etc. So typically that causes delay. As soon as something is lost, you have an overall delay that may not be needed. And as you know, web page loading is one of the major problems, is the latency, the time it takes to load a web page. For example, if you do a Google search, you would like that your Google search is not delayed because of, I don't know, whatever graphical element of the Google page has been lost. We speak very often of TCP server. What is exactly a TCP server? I close in 5 seconds. And obviously the correct answer is the first one, which you all found. So let's move on. Why do we have both TCP and UDP?
Because maybe we do not care about delivering the data in order, but we just want to deliver it as soon as possible, as little latency as possible. For example, video call.
Okay, because we don't care about delivering data in order, but we would like to deliver them as soon as possible. For example, video, that's a good point. Nonetheless, for example, YouTube doesn't deliver video on UDP, although it does, but on QUIC, which is a variant of TCP. So if it had to choose between barebone UDP and TCP, it would still use TCP. Why is that?
Because YouTube service is a bit different than VoIP. Because when we didn't receive a packet on YouTube, we can still wait. However, when we are talking with somebody, we told A, B, C, and if we lost B, it's already like lost. We just should put in the speaker A, C, and that's it.
Exactly. So video streaming has a big difference with voice over IP or even video conferencing. It is the delay. When we speak interactively, the delay to have natural conversation depends on the periods of time. 20 years ago, we said it had to be less than 150 milliseconds. Today, we are used to large delays, so perhaps people accept 200 or 300 milliseconds. But if you talk over a Skype call, for example, that has a bad delay, the conversation is half duplex. Whenever you talk, you need to wait to make sure the other guy has heard something. Otherwise, you have collisions. That makes the conversation very awkward. It's what you see on TV. When a journalist is interviewed on TV, usually they have very high quality audio connections that have very large delay, and you see this delay. When one speaker speaks to the other speaker, you see that the other guy doesn't seem to understand anything until 1 or 2 seconds later. So this is a nuisance for voice over IP, in which case you would use UDP typically. When you do video streaming, it's not real time, in fact. If you watch a football match on video, you probably are a few seconds behind those who watch it on terrestrial TV. And that difference in time is due to packet buffering. So one way to avoid the problem due to delay is to buffer the packet on the receiving side. When I receive data, I put them in a playback buffer that contains, for example, 20 seconds of video. And then I read those 20 from this buffer. If there is a large delay and a burst of video is delayed, then I will take more from the buffer. But it's only if there is a gap of more than 20 seconds, if it takes a large number of losses, that I will see an interruption. This is how most video streaming applications work today. Of course, there are other applications like DNS. With DNS, we don't use TCP.
It's very short, and we have three-way handshake and DNS responses.
Exactly. Overhead, you're better off sending, hoping it doesn't get lost, and if it gets lost, do something about it. That will cost you about the same thing as preventively opening a TCP connection. So the overhead is a reason here. Another reason is multicast. Multicast is a form of distribution where an IP address corresponds to a group of destinations. We'll talk about it very soon. And in the lab, you will have to program to multicast sockets. Multicast doesn't work with TCP. And there's a very good reason for that.
I think TCP is stateful, and so there's a window size and a sequence number for connection.
It is stateful, there is a window size, sequence number, all that stuff. So a TCP receiver keeps state information that depends on how a sender, on how the receiver is, and vice versa. So if a source is sending to 1 million receivers, then it would need 1 million windows to know which, to flow control the 1 million receivers and know exactly which has lost something and which not. So clearly, it's not efficient to use TCP for multicast. What could you use for multicast? If you are streaming data, for example, over a satellite link, where you send information to 1 million receivers and you want things to be delivered reliably. You would do UDP, but still you want...
And then we have some intermediate very wide buffer with TCP.
Mm-hmm. If you're distributing TV, probably you can live with a few losses. We see that on if you receive digital TV. Sometimes the picture is blurred. I mean, you've lost some packets, but...
You cannot put TCP on a satellite link anyways unless we have an uplink.
If you use broadcast, but for example, assume you're downloading a new version of some software and you're broadcasting it to 1 million receivers over some mechanism. So, of course, one way to do it is to have a server and a collection of server farms that will connect the 1 million receivers. You can do it point to point. If you really want to do it in multicast mode, then you need to be a bit smarter for the connection, for repairing the packet losses. If a packet is lost somewhere, you don't want that 1 million receivers send a feedback to you saying, I have lost one message, because the source, the server, will be overloaded with that. Typically, what is used is coding, Reed-Solomon codes or fountain codes, coding methods that use parities. If I send a stream of 10,000 packets, I can send, in addition, 1,000 parities with this effect that anybody who has received 10,000 out of the 10,000 packets plus the parities can decode all the data. So what fountain codes do, for example, they send the original data, then they start sending random parities for some time until and then they poll the destinations, and and with high probability, everybody has received enough. If one destination has not received enough, they continue sending parities. But the polling mechanism is also made in a way such as avoiding that everybody responds, right? How can you do that? If you're asking a population of 1 million, have you all received my information? And you don't want to receive 1 million answers immediately. How would you do that?
You could ask the receivers to convert the data with each other, or ask the other receivers where you got the message.
Exactly. You could ask receivers to talk to the neighboring receivers to agree on some joint consolidation, or what is used with the reliable multicast protocols, you use a randomized timeout. So if I ask you, have you received it? You draw a random time, a bit like we saw in CSMA CD. You draw a random time before answering, right? And you listen to the answers. So if you can listen to all the answers, then if you hear someone else saying, I have not received it, before your timeout expires, you don't send. The receiver will receive that information, and that's enough. Well, that was the topic of all the kind of things you need to do if you want to do something like TCP on multicast. But back to TCP. What we have seen is a very simplified story of TCP. We will not see the complete story of all details of TCP. We will see a large amount of details when we talk again of congestion control. I mentioned already that TCP controls also the rate at which we can send data, so we'll come back to that. We'll see a few of the bells and whistles that TCP does. I have mentioned one, when to send a packet, for example. Nagel's algorithm is a typical algorithm that is enabled by default, is disabled if you choose to disable on your TCP socket to avoid sending very, very small packets here. There is the same problem on when to send an ACK. If you have a source that for some reason sends you 10,000 packets one after the other that each contain 1 byte, you probably, as a receiver, you don't want to send 10,000 ACKs. Perhaps it's sufficient to, once in a while, send an ACK that is ACKing all the things that you have received. So there is also an algorithm to decide when to send an ACK, and it is, as you can imagine, you typically wait a bit before ACKing. Because if you do it immediately, you might create too much traffic. Let me skip this one. We will talk of primarily two, and also very shortly on this. How to detect packet loss. We mentioned timeout, but this is not very efficient. Most losses in TCP are detected by other mechanisms. And then we'll talk about a few optimizations on how to avoid, for example, SYN flooding, or how to avoid the three-way handshake totally. Voilà, we'll do that after a break. We resume at 1:15. The first issue is packet loss. Right? One way to detect a loss in TCP is to start a timeout for every packet sent. But perhaps we could do better. For example, we could say that a packet is lost when we receive a duplicate ACK. Here, for example, those two packets are lost, and we receive an ACK, and in this ACK there is a selective ACK field that clearly says that we have received this, but not the other one here. Would it be a good idea to use that as an indicator that a packet is lost? What do you think? I close the poll. So there are two polls in parallel, the poll for this, and another one about the language of the I don't know, right? Leave it to you to find out. That's easy to find. This is an example where there's no real good reason. I would say both A and B are correct. I mean, C is clearly not appropriate. C is clearly not appropriate. If we receive an ACK, well, it's a fact. If it gets lost, we don't receive it. But if we receive it, there is indication that something has happened. But could this thing be a loss, or could be an out of order? That's the ambiguity. If we are certain that the internet preserves packet order in 100% of the cases, then we would be sure that there is a loss here. In fact, this is more or less how TCP was created. TCP was imitated from previous protocols of the same type called SLDLC or HLDLC that were made to provide reliability hop by hop on a physical link. On a physical link, there is always order preservation. So if you receive an acknowledgement for packet 3 following packet 1, you know if you receive packet 3 acknowledgement, packet 2 was lost because packet 3 must have been received after packet 2. Here, it might be that those packets are simply late. They have followed another path, for example, because there is equal cost multipath routing in the internet, although we would like to avoid this. So in some cases, it may happen, so it might be a bit risky to declare that this is a retransmission. But most of the time, it's probably correct. What standard TCP versions have implemented, this is called TCP Reno version, is to use duplicate acts as a symptom of a packet loss, but be a bit conservative by requiring several packet successive duplicate acts. For example, here I'm showing an example where packet 3 is lost, so therefore we receive an acknowledgement here at time 3 and 4. We receive duplicate acts, and here if I have received 3 duplicate acts, a duplicate don't mean they are exactly the same. The SAC field may be different, but by duplicate acts, what is meant is that the ACK field is the same. So here we have 3 packets that don't advance the ACK field because there is a gap. So when we have received that a number of times, so how much is that number? By default, typically 3, but it's an operating system constant that you can modify. Then here we would declare retransmission. So this simple thing has a name. It's called fast retransmit, and it was considered a major advance in the internet when TCP incorporated fast retransmit. Its performance became much better than simply based on timeouts. But because we have timeouts anyhow, we need also timer. So how do we set up the timer? Well, TCP measures a retransmission timer by measuring the time it takes between sending an ACK number, a sequence number, and receiving an ACK for this sequence number. So it measures the round trip time, which is something easy to do as long as you don't want to, you don't need extremely high accuracy. This estimation is done using those formulas here, which are a kind of exponentially weighted moving average. I will just show the effect of it. If this is showing here the true time it takes, this is a simulation, it's not a trace, so I send a packet, I draw a random time before sending and receiving the acknowledgement, and the time I'm taking, you see, oscillates a bit, then for some reason increases here, then decreases, and the estimator of the round trip time reacts to any variation. It reacts to the variance of the successive round trip time, so whenever it increases, in order to be safe, it also increases its safety margin, so that the round trip time estimate is very sensitive to fluctuations in the round trip times. Fluctuations in round trip times come from buffers along the path, possibly also from lateness at the destination. Question?
What's going on in 91? Is the round trip time is going down, the estimator is going up?
Yes, that's on purpose. It's because the variance, now there's a large variance, the round trip time was constant equal to that, then suddenly it comes here, so because it computes the variance, or it's not exactly the variance, it's not square, but absolute values to make them, originally that was meant to be done in the operating system by very, very simple operations. So that's because it considers there is a variation. If there's a strong variation, it's suspicious, so it's treated as let's be suspicious. So this is how the round trip time estimate works, and we see that as soon as there is something changing in the network, it can become very large, which will, of course, be a supplementary justification for using fast retransmit because the timeout might not be very reliable. So fast retransmit improves on simply using a timer, but does it always work? I close the poll. And the majority says C, which is probably correct. Certainly, if the data you're sending is the last one, then if it's lost, there will be no repetition. If it's the last, not the last, but the last but one, if there are 3 things to send and the second is lost, then you need 3 duplicates, which you will never have. So that works well for streaming applications that send a large number of packets and once in a while have isolated losses that will be very well detected. But if you have short sessions, for example, you do a Google search, you open, you go to Google, you do a search, then probably the information that Google is sending to you fits in 3 packets typically. So if any of the 3 is lost, it will be detected only by timeout, not by fast retransmit. So you need better things. One of the better things is tail drop detection. So if the very last packet is sent, some heuristics will use a different timer for the very last packet, a more aggressive timer, taking the risk to have a timer that's slightly too short if you have some indication from the application that this is the last here. That's one of the optimization that's done. Another optimization that we will see in more detail is called recent rack, where here it's keeping the same idea as fast retransmit, but trying to be more accurate based on today's internet. Today's internet is characterized by the fact that reordering is a rare event and is short. When reordering occurs, it could be because there are equal costs, there are multiple paths between a source and a destination. But we will see that if we have multiple paths, in many cases, we will try to avoid sending packets of the same TCP connection on multiple paths. How is that possible?
Expecting port numbers?
By expecting TCP headers in the routers. So many TCP headers, many routers will do that if they can. If they have access to the TCP headers, they will inspect them and try to do what is called per flow load balancing. They will send the different packets to different destinations on parallel paths, but making sure packets that are likely to belong to the same TCP connection are sent on the same path. So nonetheless, some retransmission may occur. A typical case is when you have reboots of something or a change of route. Now, a complex network, changes of route somewhere might not be extremely rare. If that happens, the operating system needs to estimate what is the reordering window. So the reordering window is an upper bound on how much you think that reordering can be. Reordering means the time difference that is due to reordering. By default, if you use this option, it's set to 1 millisecond, which is a small number, but for high-speed networks, it's believed to be safe. And if you use this option, of course, if there is any evidence of reordering, there is evidence of reordering when you analyze when packets are received with all corrections of all losses at destination. At the destination, you can measure the amount of reordering. If this is larger than 1 millisecond, you increase this quantity. And then, if once this quantity is set, you will use the following heuristic to declare a loss. We declare that a packet is lost at the sender. Of course, it's the sender that needs to detect a loss. Whenever an ACK is received for a packet that was sent after this one, plus the reordering window. Let's see an example here. Here, packet 3 is lost, and we saw that before, in order to detect it as lost, we needed to have received the 3 duplicate ACKs here. But now with this thing here, it's very likely that at time A4, when I receive an ACK for packet 4, right, packet 4 was sent later, A4 is received, and if the time difference here is larger than the reordering window, then, I mean, if we think that the reordering can make you gain at least at most 1 millisecond, for example, and if this is larger than 1 millisecond, then you know that this packet is lost. Of course, if this difference is very small, you don't know, you're in the gray zone, but very often this is not the case. So in a case like this, as soon as you detect a single duplicate acknowledgement, you will know that there is a loss, which will be a way to avoid the problems of, for example, if those 2 packets don't exist, if you had sent only those 4 packets, you will detect certainly not the last but one. So this is an example of one of the many options and variants that exist in TCP. So if you have TCP in Linux, you have to see which kernel of Linux you have, and even in which kernel, you have to see which module you're implementing. You have a whole flurry of different variants of TCP. Windows tends to develop their own TCP versions that are also very sophisticated, and Apple the same way, and Android, etc. So everybody's trying to follow all those improvements. Here's another one that is implemented in most Linux machines called SYN cookies. What is the problem? Well, we've talked already of a SYN flood attack. We've seen one of the interests of having the 3-way handshake is to protect the server against a SYN flood attack. In fact, it does some protection, but still, it doesn't completely solve the problem, in the sense that when a server gets a SYN packet, if there was no SYN and SYN ACK and 3-way handshake, a server would immediately start doing some work, doing some application work. That would be making the server very fragile. So with TCP 3-way handshake, what the server does is keep state information about the remote destination, the remote peer. But even that, for very highly loaded servers, might be a risk. State information means there are kernel operating system structures that are kept. And of course, if you're doing a denial of service attack on this server, you will send SYN packets for hosts that don't exist. So the server will keep opening, preparing the opening of sockets by keeping state information, and will keep that state information until it has evidence that this will never continue. But if the timeout is not small, which typically must be at least a few seconds, it will keep the state information for all this duration. Now, if you bombard the server with tens of thousands of SYNs per second, then the server is busy with several tens or hundreds of thousands of the so-called TCP control blocks that are practically making the server unable to respond to legitimate packets, right? In the language of the sockets, it's the listen queue that is full, and the legitimate SYN packets are dropped, which means the server is unreachable. So what is a possible fix to that? Well, it's always the same idea. It's an interesting idea to see, because it's used in many instances when you have security problems. You can avoid keeping state information if you use some cryptography. State information means it's like keeping a cookie. I've had an interaction with someone. I keep a cookie such that when I see this guy coming back, I know, oh, it is this guy. It's not some random other person. But instead of keeping the cookie, I can compute something that is with a cryptographic function that is very hard to forge, such that if somebody shows me this information, it can only come from me. But if I do that, I don't have to remember, because if I have the cryptographic means, I can verify when it comes that it really, this long stream of bytes was really written by me. So that's the idea of the SYN cookies. So how does it work? The TCP server deviates from the normal way of doing TCP. It doesn't keep the state information when we receive a SYN packet. Instead, so the SYN packet contains information like what is the initial sequence number of the other end. It may also contain some other state information that is, for example, the maximum packet size, the MSS. Well, the state is not recorded, but instead is encoded in the sequence number field. So the sequence number field that the server chooses. Remember, when you open a TCP connection, each side of the connection has to choose an initial sequence number, which typically is a random number to make things harder to forge. Now, if you are the server, what you will do is you will use a cryptographic hash function where you will hash some local information with the state that you should remember. So you have created this number that you can recreate easily. If somebody shows this number to you, you can easily find what is the state because you have the hash function. And if the SYN packet was not forged but was a correct one, what will happen? The remote end, the peer, will ACK my SYN ACK, so we'll add +1 to my sequence number. So I'll receive back a sequence number that I can easily verify because I have the secret key that I've used to generate it. So I can easily verify it, and it contains some information which is also the maximum packet size, which is coded on 3 bits. So I can recover those 3 bits by trying all the 8 possible values. So when I receive the SYN of my SYN ACK, I have 2 things. First, I have with overwhelming probability, I know this SYN has been sent by somebody who has received exactly my SYN ACK. Of course, it may be by accident that the sequence number has appeared, but this probability is astronomically small. And second, I can recover the main information, which was the MSS, the maximum segment size here. So here are all the details that are given here. So this number Y that I sent is what I sent before, right? So if the SYN was bogus, if the original SYN was wrong, there is still some damage to the server. There is no complete elimination of the problem, but the damage is reduced to loss of computing power. The server has had to compute something that it needs to return, but it has not used storage. So there is exposure to the computation, but no loss of listen queue availability. Question?
What happens if the handshake is not done? Does the extra socket actually get created, or is it just not?
No, of course. Of course, once you do that, you don't create the extra socket. You will create, you create the socket anyhow when this ACK is received in the normal way. So here, when you send this, you create nothing. So the server forgets about sending this.
So when on the application you just write accept, this will just loop until actually your handshake is successful.
So when the application does an accept, and if nothing comes back, then no connection opening is coming. So for the application program, the SYN is not visible. It is as if it had not happened, which is desirable. Yes?
What is T?
Of T and client IP address. T, if I have been 3 bits, secret server key of the time. Right. Quick question now. If, like in the case of an attack, or simply a case of a packet loss, the ACK here is not received, and now I'm assuming a server that does not implement SYN cookies. I said that Linux machines typically implement SYN cookies. In fact, what you see often is that by default they have SYN cookies, but it's not activated. and when the rate at which they start receiving SYN packets is increased, so when they receive many, many SYN packets all of a sudden, then they start activate SYN cookies. So let me assume here we're in a mode where SYN cookies is not activated. But the packet is lost. So you're a legitimate peer sending packets to the TCP server. The ACK here is lost, right? What should the server do? Retransmit the SYN ACK, keep state information until a timeout occurs. What of those two things will it do? No. One. I'm sorry. One. You should put E, and of course we need to add the possibility to do both. Which needs I need to repoll because I don't know how to add. So let's restart. Well, now we have 5 possible answers. Let me close now the poll. So the majority thinks B, which means 2, which is certainly true, but A, 1 is also true. Right? That's the normal thing of TCP, right? If you send a packet, then you wait for the ACK of this packet because you're never sure whether this packet will be received. So a normal TCP server that does not implement SYN cookies, when it sends the SYN ACK, which is this packet here, waits for an ACK. If the ACK doesn't come, it will retransmit. Question?
Is there not a risk of overloading some other server with like arithmetics and SYN packets? Spoofing is an IP address to that another server, and it sends a lot of SYN packets to other servers in the internet, that these servers all send multiple multiple SYN-ACKs to the target.
You can also overload a target by receiving SYN ACKs. That's also possible. But typically, what will happen if you receive a SYN ACK and you have not sent the SYN? You will ignore it. You will receive, but you will silently drop it.
But if there's a lot of the attacker does this to really large number of servers,
Of course, you can always, by sending a very large number of packets, you can overload systems by simply reading what's the header of the packet, certainly. But here the damage is still limited to that. If you send to somebody who did not send a SYN, you send a SYN ACK, this one will ignore it because it's in the wrong state. So it will not keep state information, it will not do any processing other than analyzing the packet that has received. Whereas in the reverse direction, if you send SYN to somebody, then and if that somebody is a server that does not do SYN cookies, you create a lot of work for this server, which goes well beyond analyzing what is coming in. It goes into allocating buffers in the operating system, starting timers, just in case this packet is lost, and retransmitting. Right? So this is what will happen. Now, if we do SYN ACK, of course, if we do SYN cookies, of course, the server here will not do that because the server is stateless in this phase. A SYN cookie server, when it receives a SYN, sends all the information encoded in a cookie, which is the sequence number, and forgets about this. So if nothing comes back here, which could cause a problem in some cases. Can you imagine cases where an application doesn't work because SYN cookies is implemented?
SYN ACK gets lost.
Yes, but if we do that over for HTTP, for example. This is an HTTP client. What happens after the ACK is received? Normally here, you send. So the problem is what happens when 3 is lost. Right? But when this is sent by the client here, the client will normally send some data. Right? So it will resend. The client will verify and will resend. If 3 is lost, if 3 is lost, the server will respond if it doesn't do SYN cookie, will not respond if it does SYN cookie, but the client, if there is a client here, will also, if there is no data here in this one, that's the end of it. When we send an empty acknowledgement, we don't acknowledge the acknowledgements, because otherwise we would also need to acknowledge the acknowledgements of the acknowledgements of the acknowledgements, etc. So we don't acknowledge the packets that don't contain new data. But normally what happens is the blue lines here. If I am a web navigator here, browser, here I will send an HTTP GET or POST or something, which contains data. So this one will call for an ACK. And when this comes here, when this data is sent, it's like a repetition of this ACK, because there is always an ACK field. So if this is lost, this one will take over. So in these cases, there will be no problem. But can you imagine a case where this does not happen? Well, you need an application where it's the TCP server that speaks first. It seems weird. You open a TCP connection with a server, and the protocol says, the application protocol says, the first message that is sent is by the server. Right? Which is possible. Right? For example, the SSH, some versions of SSH do that. Some versions of MySQL do this. So the client opens a TCP connection on a given port on a server, and the server says, hello, who are you, what do you want? Right. So if that happens, there is no blue line here, or the first blue line comes from the server. But since the ACK is lost, the server never responds. So in the case like this, the application hangs. This one hangs. That's a price to pay to have SYN cookies. That's an example of the kind of problems you have when you try to solve problems in the internet, because you're trying to solve a problem of TCP, and you say, well, there's an obvious way to solve it, let me do this. But then you have to think of all the possible applications that have been using TCP and IP and the rest the way they were before. The compatibility with all the existing thing is the problem as soon as you change TCP. This is one of the reasons for people to invent things other than TCP, saying, now if I do my new thing, my new TCP or QUIC or STCP or things like this, an application that is made to this new protocol has to know the special things that this thing does. Right? So for example, if from the beginning we said TCP always implements SYN cookie, then it would be illegitimate to write an application where the server speaks first. That would be rules of the game. Then there would be no problem. But that's not the order in which things were developed. Right. Let me skip this one and mention following improvement that is also, for example, implemented on most Microsoft in Microsoft Windows 10. It's called TCP Fast Open. So it is saying, well, I want to avoid the three-way handshake, but of course I cannot do it if I have because we've seen the handshake serve some purposes, for example, identifying that there is really a client that responds to this address. But there are many cases where you have repeated TCP connections. For example, when you're connected to a server and the server will typically send you the information and close the TCP connections. Servers like to close things as soon as possible. Why? Servers don't like to keep connections open for very long if nothing interesting happens on the connection. They prefer to reopen a connection later, even if they have to pay for a new three-way handshake. Because servers, one of the very first things they want to limit is the amount of control blocks they keep, the amount of state information they keep about others. So instead of keeping state information, what many application servers do is cookies. You know those infamous cookies. They keep some memory of who you are, and they send it to you, to your browser. So whenever you recontact them, the server has forgotten about you, but sees this cookie and says, oh, this is this guy. Here is the things he has already started to negotiate with me. So let me quickly find in my database the thing that this guy has started. So servers try as much as possible to be stateless by pushing out the information. Therefore, they will tend to break TCP connections very quickly. You do something with a server, even if you're ordering, for example, a long list of items on the IKEA website, it is possible that it breaks the connection several times. And whenever you reopen a page or you change the page, it starts a new connection. If you are in a case where you have repeated connections, then there is this proposal called TCP Fast Open, which is, as I said, implemented in many systems, where you want to avoid the latency of three-way handshake for something that is with a client that you have contacted already, so you know it exists. So that's the same idea I said about cookie. So here is in detail how this cookie is done. You compute using a cryptographic hash function. You compute what is called a tag, which is a hash function, is something that computes a number between 0 and 1, or a sequence of 64 bytes, for example, that appears to be completely random, but is in fact completely deterministic if you know the key, the secret key. So you hash the IP client address C here with your secret key, and you cache this cookie here, and you give it to the client at the first time this client connects. And when this client reconnects with you, then you ask this client if it supports TCP Fast Open. In a TCP option that is possible to put in the SYN header, you put the tag here. So when this TCP server, which is now a non-standard TCP server, when this TCP server receives the SYN packet, it immediately it forks and immediately opens another socket. And if the program doesn't accept call, immediately after the SYN is received and the tag is verified, the forked socket is available and is open. So that you can already send, for example, the GET message here. The rest continues as before, but the effect is that you've started sending the first message in the first packet, so you have what people call zero RTT communication establishment. Of course, there are a few details you need to verify. This tag should not be valid forever. Otherwise, anybody who has this IP address can communicate with you at any time. So, of course, there are typically short timeouts associated with the value of the tag, which can be also contained in the tag itself. Voila, those are three small variants of TCP that exist. We will see more when we talk about congestion control. There are more algorithms in TCP. That gives you a flavor of the complexity of TCP. Complexity compounded by the fact that anything you change to TCP must be backward compatible. But before getting to how we can improve TCP or go other directions, which we'll see a bit later, let us come back to a fundamental question. Why does TCP or other error recovery mechanism operate the way they do? And this is a historical question. And the problem is, how do we handle, originally the problem was really physical layer losses. So when a packet is lost, for whatever reason, how do we repair it, right? Well, in TCP/IP, the design decision is that every layer other than the physical layer should offer an error-free service. So packets are either delivered without error or discarded. In theory, we know from information theory, we could do things differently. We could have a few bit errors and add redundancy and various coding forms in the payload to detect them, but we don't do that. We see also, for example, that an Ethernet adapter, what does it do if there are some bit errors in the packet?
Try to do error correction.
You will try to do error correction, but most likely you will simply detect the error with a frame check, FCS, frame check sequence that is at the end of the Ethernet frame. If there's an error, the frame is considered invalid and is discarded. In contrast, on Wi-Fi, there is a similar thing, but if there's an error, Wi-Fi decides to retransmit. You send a packet, there's an error, so you don't have an acknowledgement, or you have a negative acknowledgement, you send it again. We do that on Wi-Fi, we don't do it on Ethernet. So in some sense, we see now several things. I mean, we see that TCP repairs the errors, but TCP is end-to-end. Wi-Fi repairs the errors locally. Ethernet does not repair the errors locally. So why does one do this way? Why others don't do it this way, right? So the question is, if I have a case like this where packet 3 is dropped for what transmission error or whatever other reason, Wi-Fi does this. It's repaired locally, so that's called hop-by-hop reliability. Whereas if we have only Ethernet everywhere, the loss, even though it's on the first link, will be detected only at the destination. So if I send a packet to a web server, I do a post to a web server that's in California, and the packet is dropped here on the Wi-Fi network, it's only the, sorry, not on the Wi-Fi, but it's lost on a link between two routers on the EPFL campus. It's only the server in California that will detect it, not locally here. So why do we do one way or the other? What should we do and why? Right? Is it a good idea to do this? Right? Well, let's examine the arguments. There is a good argument for end-to-end error recovery, right? The first argument is, that's really the heart of TCP/IP. This is what made TCP/IP successful. That was this idea that we separate TCP and IP. At the very beginning, before 1979, TCP and IP were in the same protocol. We transfer packets, and at the same time, we verify if they are well arrived. But then we've seen that we do something else. We do packet switching with the IP principle, where every unit, every packet has its own address, and it's transported as an independent entity. And the reason is to keep intermediate systems, the routers, as simple as possible. And that was very effective. But if you look at this little cartoon, you see also something, right? Something that speaks against repairing packets hop by hop. What is that thing? Well, we've seen here that this transfer of 7 packets was using multiple paths. I've said, and we'll repeat that, very often we try to avoid this, but it's not entirely excluded. So if a packet is not visible here, it doesn't mean that it's lost. So if we do hop-by-hop recovery, and we're in a case like this, then it doesn't make sense. So you can do it in Wi-Fi, where you know there is only one path between you and the Wi-Fi base station. But if you're in the middle of the network, between two routers at EPFL, you don't see packet number 3. You don't know whether you don't see it because it was lost, or because it was simply sent over some other principles here. So that speaks against doing hop-by-hop packet recovery. But we will see that there are another argument for speaking in favor of hop-by-hop recovery. But this is a longer story, and we will see it next week.